Zu spät dran.
So, jetzt müsste wieder laufen.
Sie befinden sich in der gemeinsamen
Bildschirm.
Bildschirmnutzung.
Whatever.
Habe ich auch lange, wenn man einfach sowas nicht gesehen hat seit langer Zeit.
Das System ist,
jetzt einfach.
also wie gesagt, ich habe das komplette System damals so von der Uni geerbt und seither ist es so.
Yeah. Okay.
Okay.
Actually, now the connection is good. Oddly, no?
Okay.
Good.
Okay.
Okay.
I'm not sure if he actually intended it as a gag, but
The sad thing is that students don't get most of this. Hitchhiker's Guide to the Galaxy. No one knows them. It's amazing.
Really?
Yeah.
okay.
Ask it. They're 42. Stop. That's a good one. You're a nerd. That's great. But they're all supposed to be nerds.
Okay.
Yeah. And if you ask them in very, if you've heard or read it.
Yeah.
Okay.
Good.
So
Sorry, I just heard it.
There's a finite.
I'm not surprised of one.
No, that's the main thing is I couldn't even do it if I wanted to because we cannot speak at the front conference that during the wine tasting, which is really, really good. I organize a wine tasting.
You will make a restart.
so just reconnected or
Make a restart.
okay. Okay. So it's the projector, not my PC. Okay. Okay, that's fine.
Maybe the cable.
The cable?
Βγάλαμε το ξαναβάλαμε το καλώδιο.
Now it's coming back slowly. Okay, the beamer is basically warming up, right? Or is it?
It's not alive. So
Yeah.
The projector is warming up.
Okay.
Just watch out for the cable because there's going maybe it's a little bit.
Okay, it could be. Okay. Okay.
So, welcome back after a little bit bigger meal today compared to yesterday at lunchtime. Hope you enjoyed it. So, we have the next lecture in the series of interferometers. Before we start with that, I hope you've all put up your posters for today. You checked that you have today, and those who speak today have it up there. If not, at the end of this, during the coffee break, please do so. Okay? Good. So.
Okay, so well, Enno has partially introduced me in his first slides a few days ago, and today I will be telling you about what can you do with the stuff Enno showed you, and how you actually can apply that to yeah, some nicer things like, for example, gravity gradients, and maybe in the end we will come to rotations. And well, just to give you a quick kind of tour of how I got into all of this is basically at some point I was sitting in a lecture by Professor Schleich and Enno, and basically learned the initial stages of all of this. And well, we ran from there, and over the years, lots of people have helped building basically the mathematics and tools to actually describe all these things. Okay. And yeah, in the end, starting from some initial basically papers on the Marcinger interferometer, all of this has moved into actually describing very complicated things, for example, dark matter stuff, and also maybe even gravitational waves and stuff like this. And yeah, so let's start with the stuff Enno basically finished with. So I will return basically to the branch description, and what we will do now is we will take this branch description and see how we can basically implement small perturbations in there, how we can calculate the phases for that. And I will give you a quick outlook on what you can do with wave packet effects later on. That will be part of the second lecture. So, okay, so as we have seen this morning, so this is a quick revision before I start with the basically writing it down step-by-step part. We have seen these branch-dependent description where we have these evolution operators for the external motion that emerge naturally from actually multiplying matrices and basically taking this backwards and then constructing paths or branches from that. So just to actually highlight this a bit, so there are basically two cases here. Enno has talked about the, so to say, single photon case or single photon AI case. And in that case, the branches basically emerge because each of the interferometer branches is correlated with an internal state. So, for example, this picture of the Marcinger interferometer here, where you can see basically you come in with the ground state, and then during each part of the branches, so to say, happening, you are correlated with a certain internal state. So you can track by internal state and momentum transfer on which branch you are, if you're on branch 1 or branch 2 of the interferometer. So there are more complicated things. I will not go into detail of that. Enno mentioned it a bit. So Bragg, or for example, lattice-based AI. And there you basically have to track the branches by the kicks and momentum transfers happening. In any case, what we have seen before is that the sequence of time evolutions basically along a branch here is basically given by a sequence of external evolutions, and in our simple case with the instantaneous pulses, basically the momentum displacements. Okay, so, and the signal we determine at the output port of an interferometer, we have written in terms of this overlap operator, which I call O to 1. And this is basically the path evolutions 2 and 1, and the backward, the evolution for path 2 is basically going backwards because we have the adjoint here. And what we've seen, well, we haven't seen that only for the basically open interferometer, that there's a visibility here, and we have a phase, which basically determines our interference signal. More generally, and I will go into that during the week, is that one can also have different basically, well, exit port observables by actually adding a measurement projector or something, a projector which describes the measurement you're doing. So what we've done up to now is basically we've taken integrated particle number, which is up here, right? So we integrate over all of space and project on all atoms in the ground state at the exit port. I've illustrated that here basically by putting the detector up here. Okay, so let's go back to the path evolutions from before the break or this morning. And there we had basically U1 and U2. And for U1, we basically had, we come in, get a kick, then we evolve freely for some time, t, basically, and then we go straight, and then we evolve into the exit port. So this gives you this line. And the second line, you have external evolution first, so we go straight, then we go basically give a kick, have some evolution given by the, so to say, clock phase happening, or clock phase evolving in that first time interval t. And then we basically kick our atoms, propagate again, do the internal propagation, and then we kick again into the exit port. Okay, so as a note here, and I think Enno has also mentioned this before, and some of you have actually said, or we have talked about that during the poster session, that the clock phases, technically, if the interferometer is not a Marcinder interferometer, which is closed, they can have a severe impact, and then you actually have to carry them through the calculation. And you can do that by actually absorbing basically these clock factors here into the respective external evolutions. What you would have to do for that is basically you take your clock phase and your internal, or your Hamiltonian for the external motion, that guy here, basically gets the internal energy and a unit operator in center of mass, plus the usual external Hamiltonian, meaning p squared over 2m plus the potential for your problem. And well, yeah, then each and every one of these guys can be replaced by these u external in the given state L. Okay, so with that, we have seen something which is kind of a cookbook now, and we will use that to a great extent now. Namely, what one usually does in interferometry, or in the description of these interferometers, and Enno has hinted at that earlier this morning, basically, you write down a geometry, something like this up here on the right, this here. And what you do is basically you determine the branches, multiply operators along branches, and calculate your result. Okay, so what I will show to you now first is that we can take the Marcinder example, basically generate a very general rule to actually determine arbitrary geometries from that. So first point would be draw your spline diagram for your geometry of choice. And then you go, okay, second thing is we write down the path the path evolution operators, basically. The UJs along the paths. So the first thing that we have to do to order to show this is basically that we have to determine the effective Hamiltonian we have along a branch or an arbitrary branch. So our goal would be basically show that the operator sequence arises from an effective Hamiltonian. From H effective, just H effective of your path J. And for that, what you do is basically this thing should have the form in the end after we have basically shown that step by step, that this is given by some external evolution depending on position and momentum, plus a kick potential for your branch. And this thing here determines the overall kind of Hamiltonian, right? And as I mentioned before, for the clock interferometers or single photon interferometers, basically you can hide the internal energy along a certain branch, or how the internal energy changes in here. So this is basically EJ plus H external of Z and P. Okay, and what we want to show now is that this guy here actually is given by H of Z and P minus H bar times the sum over L over some quantity lambda L. Which is Kz plus the laser phase at time t times delta of t minus TL, which is the pulse time. Okay, so some comments. What is this kind of kick operator doing? Well, we kick, right, of J, of Z, and T is your momentum transfer. So what Enno also called the displacements, basically. So transfer momentum and imprint the laser phases. Onto the branch J. Okay, and the thing is, this only affects one branch. So just as a convention, we have for the lambda L of J times H bar K. This is the momentum transfer. And the momentum transfer for each individual pulse actually depends on the kick direction. And you have basically lambda L of J equals 1 if you kick up, 0 if you don't kick, and minus 1 if you kick down. Okay. Then one more thing, or basically the same kind of convention stuff for the laser phase. And here we have lambda L times J of H bar phi at the time TL is the laser phase imprint on J at TL. Okay, and you have to keep in mind that, just as a reminder, as you see here, depending on in which direction you kick, the laser phase also gets a plus or minus sign. So if you kick up, the laser phase gets a plus sign. If you kick down, the laser phase gets a minus sign. Yeah? Good. So one thing, so this potential, right, basically has the position operator in there. So it's a quantum mechanical potential, but we will see later on. So as a aside, the classical counterpart to this potential, right? To our V kick of J, that is just remove the head and remove the head also from the position operator, determines motion along paths, and these paths are classical paths, and these classical paths follow from the Hamiltonian equations of motion. So determines Okay, so in that case, that would be z dot equals the partial derivative of h effective j with respect to p, and p dot equals minus h effective j after dz, which is basically the external Hamiltonian, the z derivative minus the kick potential along the branch G, also the z derivative. Okay, so just keep that in mind. For the time being, we will need that basically when we get to the end of the lecture. We will make use of that. Okay, good. So what I will do now is I will show you by going into the interaction picture how actually these kick potentials arise. So what we do is we say, okay, we are interested in actually finding for or deriving, so to say, the interaction picture Hamiltonian. Okay. Okay. Okay, and when we do that, we call basically the time evolution associated with that u external of t is the time ordered exponential minus I over h bar 0 to t ds h of z and p. So if I go up here again, so we're going into the interaction picture with respect to this guy here, okay? Okay. And what we see then is basically that the Hamiltonian in the interaction picture along the branch is given by u external dagger of t, the kick potential along the branch G, u external of t. Okay. The thing we need to do now is we need to actually calculate that thing. And what we here see is basically the kick potential. That guy here, in here, is a function of the position operator. And basically what happens by sandwiching these guys here to the left and right is that we have to think of basically that the position operator Z is basically replaced by the interaction picture position operator, which is given by u external of t, the kick potential. Oh, Z, sorry. Yeah. Z u external of t. Okay. So, whoops. Let's just move this over here. Okay, good. And so what we have then is basically that we need to solve for the time evolution in the interaction picture on the branch J is simply time ordered exponential, formally minus a over h bar, 0 to t ds. And well, then we basically have the kick potential at pulse j evaluated at the position operator in the interaction picture. And well, residual time dependencies, for example, the laser phase also. Okay, now we evaluate this. Oh. Well, okay, good. So what we do now is we take the expression we had for the kick potential in terms of the delta function. So this guy up here, and we introduce that down there basically into the time ordered exponential. And what will make life easy for us is the fact that back here we have these delta functions, because they will make it easy for us to evaluate the time ordering. Okay, so let's do this. Again, time ordering, exponential, I, and basically in the exponent, we just sum over all the pulses, L, by evaluating the delta functions, lambda L on branch G, K, Zi at time TL, plus the laser phase at time TL, which I just call phi L. Okay, and basically the sum in the exponential or in the exponent can be converted into a product, and the time ordering basically takes care of the time order of things. So what we get is the time ordered product of e to the I lambda L J K Z I in the interaction picture at time L plus phi L. Okay, so again, as a reminder, what we did here was evaluate delta T minus TL, and in that step, basically decompose the exponential into factors. Okay, questions so far? This was just basically playing mathematically, and then we kind of see that this basically follows the generic procedure, so to say. So when we look at the single factor of this product, we have e to the I lambda L J, kz, again in the interaction picture at time TL, plus phi L. What we can do now is, with this, we can reverse the interaction picture. Reversing the interaction picture is actually easy, because all we have to do is basically put the external evolution outside the exponential. Yes?
Can you get an idea where you want to go?
Yes, yes, okay, okay. So what I want, okay. So the idea in going here is basically starting from something like this here. So here we had basically these sequences written down for the Mach-Zehnder interferometer. So what I want to show you now, or what's actually the goal of actually doing this, is showing you how to do this for an arbitrary sequence, right? So I want to have expressions for an arbitrary sequence, so you can write down basically any geometry you might want. Well, kind of depends on the mirror or beam splitter process, but for example, for a single photon interferometer, you could write down some really, really complicated LMT geometry by actually just tracking the two paths and actually construct this from the paths directly. So you basically, for example, maybe this is better over there. So suppose you do some really fancy geometry where you do multiple momentum transfers. Right? And what we are interested in is actually how do you write something down like that with the stuff we've learned from the Martiner interferometer. Basically, just draw the picture with the stuff you have and then take the whole thing and actually put it all the way.
Is the following. We have a unitary time evolution operator for one arm, and for the other arm. The question is, can we just write down a Hamiltonian that describes the evolution along one arm or the other arm? So actually, we want to write down a Hamiltonian that when we solve the time evolution, we get U1, and we want to find a Hamiltonian that if we solve the time evolution along with H2 or something, we find U2. And that's what he's showing.
Yeah. So essentially, I'm basically taking this backwards from basically multiplying all the U's back to the H effective. So, and I kind of started with the result in essence, right? Because I kind of said, okay, what we want to show is that H effective is of this form. And what I do now is basically I take this form and I kind of show that you end up with what you kind of desire, so to say, in the end. Okay, so yes.
About this form, why this is so important to get there? Why is this form you wrote down there?
Which one exactly?
The one you said is gold.
Ah, okay. So the guess actually, so what you do is you look at these two sequences, right? U1 and U2 you've determined for the Martiner interferometer. And what you kind of see here is that you have this exponential factor, right? Which is kz plus the laser phase at some point. Then you have the external evolution. Then you have that thing. And what you're essentially doing is basically you're kind of trying to reverse this product step by step going through the sequence and actually write this into a single Hamiltonian by introducing appropriate, basically, a stepwise defined Hamiltonian, so to say. This is the overall idea. And the stepwise defined Hamiltonian basically would be H effective here along the branch at the end of the day. Okay, so after that, set by L. Okay, so this is for one step. So basically what you see is, right, that you can basically get these phases or these sequences of external evolutions sandwiching these basically kick operators. So going back to what I said earlier is, or just a second ago, that you basically have sandwiches like this and this sandwiched by some kick. And I mean, also in here is basically the clock phase, but yeah. So we're trying or seeing that we're getting some structure like that. Okay. When we just do for the whole path, basically the reversal of the interaction picture. So the evolution along the path is then U external, basically. What would normally be your, so to say, U0 in the interaction picture. And then you have the interaction picture part or interaction picture evolution operator for the branch. And guys now basically, as we have seen by writing down these products, would be U external of T minus T L e to the I lambda L J kz plus phi L U external of TL minus basically the time of the pulse before. And so on. Lambda L minus 1 on branch G kz plus phi L minus 1 and so on. So what we see is that this generalizes actually the stuff we have done, or we get exactly the structure we have seen at the Mach-Zehnder interferometer. We can just do that for J pulses, so to say. Yeah.
Like summation index.
The L is basically a summation index, yes. So with,
here the last equation. Like a little bit confused by that. The same
what?
the equation above that the L vanished with the T, so like didn't have a L anymore. But
so which are you referring to? Which?
both of them, like in the single factor equation.
Yeah.
On the left you have TL, and then to the right you have T. Don't know TL anymore, it's just T now. I think that should be a TL next to
Yeah, should be. Should be.
And then the last equation, I don't know, I think L.
Yeah, they might do.
Should this be like the upper index of the product?
Yeah, this should be TL here. So. Yeah, that should be TLs. Okay, and then I think down there we're kind of safe as far as I see that. Because this here is T. This should also be T actually. Okay, but then we should be fine.
But the L, the last equation where the L comes from, what is the L?
In your case, right, so the L basically would be counting your pulses. So what you would do is basically you multiply Fourier sequence, and basically the L would be the number of your pulses, so to say. So yeah. So I will show the example for the Mach-Zehnder right away. So yeah. Yeah, one could actually introduce the second index, so say n pulses, and then you basically sum L to n. Okay, so what this does is basically it generalizes what we did for the Mach-Zehnder interferometer to arbitrary pulse sequences. And for example, if you then write down the kick potential for the Mach-Zehnder, that would be along the first branch minus h bar az plus phi of t and two delta functions minus t minus t1 plus delta t minus t0. And for the second, minus h bar kz plus phi of t minus delta t minus t2 plus delta T minus T1. And this is just by example again, as we had up here, supposed of this form, right? So the kick potential, right, is the green part in the back. Okay. Again, the, so to say, recipe or cookbook is draw the diagram, and then read off the branch Hamiltonians and kick potentials. Okay, so from that, that's basically the part about the branch Hamiltonians. And what I want to show you now is how to actually include perturbations in this whole thing. So basically anything in your experiment which you might be interested in, for example, small gravity gradients or rotations, or basically also any other perturbation you can find a potential for. So, okay. Okay, and for perturbation theory, what you would normally do is you would have some Hamiltonian, you know, h of z and p for your external motion, and you have one part which you can solve. So we call this h0 of z and p plus something small you can't solve, which is your perturbative Hamiltonian, hp of z and p. Okay, so again, just for reference, unperturbed part needs to be solvable in some way. Can even be numerically, so you could also use this as a starting point for doing numerics for interferometers. And basically back here, some small perturbation, and small just means epsilon is something which is smaller than 1. Okay, so what we do now is we actually apply this decomposition to the branch Hamiltonians. So for the Hamiltonian along branch J, we have basically h0 of z and p plus the kick potential of z and t plus our perturbation. Again, could be gravity gradients, could be some small magnetic field or harmonic magnetic field or something like that. Good. So, and what we do now is we take this part as the part for which we basically go into an interaction picture. So we not only take the interaction picture with respect to h0, but also take the interaction picture with respect to the kicks. Yeah. And so the aim or goal is to find an expression for the interferometer phase resulting from the perturbating potential. Okay. Good. So first thing we need to do is actually determine basically the interaction picture evolution, right? And for that, we need to find the evolution operator for the unperturbed part. So we need to find the evolution operator basically for resulting from these two guys. Okay. So again, formally, we can write this down. I will just call this U0 of t as time-ordered exponential minus I over h bar 0 to t integral over ds, and then in here h0 of z p plus the kick potential. Okay, so what will this give us? The perturbing potential here is a function of z and p, right? So when we sandwich basically z and p by this u0, then we get the interaction picture z and p operators along each branch. U0 dagger of t z u0 g of t, and the same for basically p. So we get z and p operators, which are basically evaluated on these interactions pictures along the branches. Okay, same goes for the Hamiltonian, right? So HP, or the perturbing Hamiltonian along the branch G, is basically given by the perturbing Hamiltonian evaluated at the interaction picture, basically operators. Okay, so, and these operators here are evaluated along these, so to say, unperturbed branches, because we have U0 here on the left and on the right. From that, we can determine the evolution operator for the perturbing potential. Again, time-ordered exponential minus I over h bar 0 to t ds hp j of s. And now we're almost there, because we're saying, okay, we can solve this guy. So the overall evolution, right, for the whole thing will be along one branch will be something like U0 of J times UP of J. And what we do now is basically we would take an approximation for this because we know that this guy is small and I forgot an epsilon here. And we will now just basically just take this guy and do a Dyson expansion of this. So this is approximately unity operator for the external motion minus I epsilon divided by h bar, integral from 0 to t, h perturbing the long branch j of s. So plus higher order corrections. Okay. We will have that back in a second. So one comment is in order here, I guess, that if you're, for example, interested in actually having something which goes beyond the Dyson series, which is interesting for some applications, then there's actually a nice paper by Enno and a colleague. So have a look at PRA 101 050 053 615, which Christian and Enno have written in 2020. There they basically do this with a Magnus expansion. However, the math then is a bit more involved, and it's kind of useful if you want to get wave packet effects or higher order effects, because you can go to higher orders in the perturbation theory there more easily. Okay, so what we do now is we have the overall evolution, and we now apply this to the overlap operator. So and I'll suppress the time arguments simply because then the expressions just become more complicated. Okay, so overlap operator O21 is U2 dagger times U1. And now we insert basically the decomposition. And for the adjoint, we know that we have to switch the two products in the operator, U2 perturb dagger, U0 2 dagger, U0 1, and U perturbed on path 1. Now, the thing is, if we take the initial or the unperturbed interferometer to be closed, this guy here becomes a pure phase. So pure phase and remember the unperturbed AI is closed. No? So this thing here has the following form: e to the I phi 0, u perturbed 2, u perturbed 1. So the only thing that actually stays or is left with us in the end is basically an overlap, which is determined by the two perturbing operators, perturbing evolutions, and basically the, so to say, phase from the closed interferometer. As an example, we have already seen this actually happening, right, for perturbation 0 in case of the Mach-Zehnder interferometer. So U0 2 dagger, U0, 1 equals e to the I phi 0, 1 external for the Marcinder interferometer, and phi 0 in that case, well, phi 0 is laser phase difference minus kgt squared. Okay, what can we do from there? Well, the usual thing we would do is we would calculate the expectation value of the overlap. And as we see now, expectation value of the overlap operator just is e to the I phi 0, and then the expectation value of the perturbing operators. One and the expectation value with respect to the center of mass motion. Again, what we do now is we do basically insert the Dyson expansion for both of them, for this guy and this guy. So insert Dyson, and then we're basically almost where we wanted to be, because then we have something which is e to the I phi 0, 1 minus I epsilon divided by h bar, integral from 0 to t ds. And I've taken the expectation value basically into the expansion. H perturbing along branch 1, S minus H perturbing along branch 2, S plus higher order corrections. So what we see here is that this looks eerily like we are just basically going along and basically taking or calculating the difference in the expectation values between the two Hamiltonians integrated along the unperturbed trajectories, closed interferometer, right? So in the difference of the Hamiltonians along different unperturbed trajectories. And this is the result actually, which basically first I think came out of a calculation of Cohen, Tanucci, and Story in like 1997, if I remember correctly. So although they had to do quite some, well, more complex mathematical maneuvers, basically, because they were working with path integrals. Okay, so one thing we're still missing now, right? So this is still not that trivial because, for example, we know from our quantum mechanics lectures that if we have the expectation value of some Hamiltonian, something like this, we can't simply do the following. We can't simply say, hey, this is basically, right? This is not the case. So we still need to kind of do a second step. And the second step one has to do here, right, is if we want to actually simplify this further, is we have to do a semi-classical approximation. So, and for the semi-classical approximation, what we do is we basically say the following. So we kind of determine for each branch a mean trajectory. And this mean trajectory is what we call the classical Ehrenfest trajectory of branch J. And Ehrenfest's theorem basically tells us that the mean value of the operator basically determines the, so to say, mean classical trajectory for the operator. Same goes for the P operator. Classical trajectory is again given by Pj of t, expectation value. So again, classical trajectories from basically, yeah, Ehrenfest. Okay, so what we do now is we basically take these Hamiltonians up here, these guys, and what we do is we expand them around the classical trajectories. When we do that for one of these Hamiltonians, the perturbing Hamiltonians, then we have HP, and by this basically a long line, I say, okay, evaluate it along ZL, Z classical J and P classical J, basically, plus the partial derivative of, with respect to Z of HP, again, along the classical trajectory. And now we'll introduce two new operators, ZJ plus HP, BP, delta Pj, plus the second order terms. Delta Pj. And this is the anti-commutator plus HP second derivative with respect to P, delta Pj squared plus higher order. Okay, and again, this guy is the anti-commutator. Taylor around Z's the classical J, P classical J. Okay. So again, HP simply is HP evaluated along ZL, J, P, classical, J. Okay. So what we get is the 0th order. Basically, we take a classical Hamiltonian function now, and we evaluate it along these classical Ehrenfest trajectories. So this will give us the 0th order correction. This is one. And then we also have the variances and covariances, which are basically these operators with deltas. Yeah? So delta Zj is nothing else than Zj minus Zz Cl, basically J, delta Pj equals Pj minus P classical J. Yeah? Okay. And these guys here basically describe fluctuations around, so to say, the classical trajectories. So okay. By constructions, these things have some nice properties. Namely, when we look at the expectation value of these delta operators, then we see that basically, okay, they are the expectation value for the position operator on branch Z, on unperturbed branch Z, minus Z classical J, and basically this is exactly the same, so this is 0 by construction. Same goes for delta Pj, also 0 by construction. So that we see in this Taylor expansion, the first term will naturally drop out because the classical trajectories basically fulfill Hamilton's equations of motion. Okay. Last thing, these second order terms. So delta Zj squared delta Pj squared and delta Zj, the anti-commutator delta Pj. These guys basically describe the covariances of your wave packet or your wave function propagating along one of these branches. So I will make a sketch in a second for that. These guys. So they are the covariances. Okay, so how can you imagine that? So basically something like this. This could be a trajectory in position space or momentum space. Just for illustration, I will call this high J classical. And what you have is basically, you have some wave packet. I hope I can draw that reasonably okay. So this wave packet is moving along this trajectory. And what's happening actually is the wave packet actually is changing shape. And if you assume a Gaussian wave packet, so to say, the change in shape is determined by actually the change of this guy, and this guy with time. Yep. And well, this can be in position space or basically in momentum space. And in principle, you could also look at this in phase space. There you have basically a picture of all of these covariances then. Okay, so when does this work? What's the kind of assumption going into this? Well, the kind of assumption that went into this was that and the green one, that the perturbing potential, that's actually basically in this direction, right? So potential has a very, very small curvature compared to the size of the wave packet actually moving through the potential. So the wave packet itself only probes the perturbing potential locally, but does not see basically large changes over large things, right? But naturally, by constructing the formalism along the individual trajectories in the interferometer, this is not really that constraining because we don't have to take the global thing into account. We just have to be reasonably localized with respect to one of the branches. Okay, so the underlying assumption length and curvature scale of the perturbation are much larger than the position than the position momentum width of the wave packet. The same goes for the covariance. Okay, so under these assumptions, we can even make something way more harsh than that. And actually going to second order, we just basically truncate the thing right at the first order. And what we end up with then is the thing I kind of promised you before, namely that we have the overlap operator is simply e to the I phi 0, so phase from the unperturbed interferometer times expectation value of the perturbed evolution and this guy is approximately given by e to the I phi 0. And now we again just take this as a 0th order approximation or first order approximation, 0 to t ds. And now we evaluate the perturbing Hamiltonian along the classical trajectories. ZL, that's Z classical 1, P classical 1 minus H P evaluated along the second branch. Okay. Okay, so two things went into that. Yes. Not necessarily. I mean, obviously not. So any operator, I mean, I just used that because I used the same symbol for the function earlier, but technically the thing is not an operator anymore. So you have basically the thing and you have just the classical trajectories in there. So since we did Dyson, and this looks like the first order of basically the expansion of some exponential, we kind of do the tricky thing and basically re-exponentiate this to order epsilon, and what we end up with then is e to the I, so phi 0 plus phi 1 with basically phi 1 being epsilon times our integral right? So basically the guy from above. Okay. Divided by h bar, sorry. Okay. Yeah. So what we see is minus. Yeah, minus. I forgot the minus. Okay. Exactly. So what we see is basically that the phase from the perturbation is nothing else than actually taking the classical trajectories corresponding to the branches, integrating along them, and basically taking the difference of the Hamiltonians from there. Yes.
Exponential missing looks like this.
Okay, so what I did from here to there is basically I was kind of lazy in the doing this. So what I did was I said, okay, so I basically, so the more clean way actually would be to do this via Magnus expansion or something like that, but I wanted to spare you actually the recombining of the exponentials. Okay, so what we have now is a simple way to actually calculate phases resulting from perturbations. So few comments with respect to that, and then I will quickly show you an example, namely gravity gradients. First thing is the classical trajectories of the branches may actually depend on the initial values, obviously, right? Because they solve Hamilton's equations of motion. So the initial conditions go into that. So this phase phi 1 will actually lead, in some cases, to dependence on the initial conditions. So also, these classical Ehrenfest trajectories are basically identical with the classical trajectories you would actually determine for systems up to quadratic Hamiltonians. So okay, beyond that, that's not necessarily the case. Okay. Now, last step, let's put this into practice and see what we get out of this if we, for example, look at gravity gradients. Any questions before that? Okay, you all seem kind of tired, so ready for coffee break, probably. Okay, so last stop. Okay, so in case of gravity gradients, first thing we have to do is we have to write down the perturbing Hamiltonian. Perturbing Hamiltonian is rather simple. Namely, gravity gradients are basically just the harmonic part of the gravitational potential. So perturbation Hamiltonian epsilon times h p of z in this case only is m half gamma times z squared. And this guy here basically is the gravity gradient. Gradient, or more generally, in 3D, you have something like the gravity gradient is proportional to position vector times the gravity gradient tensor times position vector. Okay, good. And what we do now is we plug this into our standard example for the Mach-Zehnder interferometer as a perturbation. Okay, phi 0, or the unperturbed phase, is actually easy. We have done that before, or Enno has done that before. So phi 0 equals delta phi, so laser phases, minus kg t squared. Then we have to calculate phi 1. Phi 1 is just plugging in the perturbation, m over gamma divided by 2h bar, then the integral of 0 to t ds over the classical trajectories, that classical on branch 1 squared minus z classical on branch 2 squared. So I'm just taking basically this guy up here, plugging everything in, and putting in the classical trajectories. And what we see here now, this is something of the form a squared minus b squared. So this will be a minus b times a plus b. Okay. And this is something nice because when we think about this, we can actually define nice variables where this thing becomes really, really easy. Namely, we define two things. Define delta z, so the difference in the two classical trajectories. And this is basically z classical 1 minus z classical 2. And we define the mean trajectory of the two classical trajectories, which is basically the central trajectory, if you want. Z bar of S equals 1/2 times Z classical 1 plus Z classical 2. Okay? And with these variables, the integral becomes a lot simpler. We take the 1/2 from the front. And now we integrate over the difference in the two trajectories multiplied by actually the mean trajectory or central trajectory. And this is, I think, something which was first derived by Christian Baudet, but I don't really know when. I think 89 or something, something like that. So. Don't crucify me on the year. Could be plus minus some. Okay, and now the only thing we need is we need expressions for that guy here and that guy here. So mean trajectory in the mass cylinder and basically the difference in the two trajectories. And in case of the mean trajectory, we basically have the initial condition plus basically initial momentum plus half a kick. So h bar k divided by 2 divided by m. This is the mean velocity minus 1/2 g t squared. G squared. I will just t squared. Similarly, for the difference in the two trajectories, you basically get h bar k over m, and this is t for 0 between 0 and big T, so during the basically first part of the interferometer, and during the second part of the interferometer, this is 2t minus t. So for t between t and 2t. Okay, all we have to do now is take these two guys, plug them into the integral, do the integration over the polynomial, and what we end up with is phi 1 is k gamma t squared times z0 plus p0 plus h bar k half divided by m times t minus 7 over 12 g t squared. So we can rewrite this a bit simply because this basically the first part is the mean trajectory. So k gamma t squared z bar of t minus 7 over 12 g t squared. Okay, and as we see, and as I promised you, basically this guy here contains the initial conditions. So what you get out of this is, if you do a single run of the interferometer, you get a phase, and I would call this the phase of the run m, which is basically phi 0 plus, and then you have phi 1 of z0 in the mth run and p0 in the mth run. And this is why people actually, or Enno has also said that before a lot, that you don't want to be sensitive to initial conditions, because each time you will basically get some phase from that. And by that, you need a lot of runs to actually average this out, if it averages out at all. Yes?
Right. The last line, shouldn't there be like something different about the 712? Because if you look at the average set, there's like a term 1/2 GT squared. And this doesn't appear when you like plug it into the second to last lines.
112, right? Yeah. Could be. No. Or, yeah.
Yeah, but there's
Okay. Good. So the thing would be is now, or the thing that one would kind of think about now is, how do you get rid of these kind of things? But I think I will tell you a bit about that at the beginning of the next lecture. But I will just leave you with one thing. So, or basically a pointer to the literature in that case. So stuff like this, or initial condition dependencies, can be compensated. By adjusting the pulses, and I will give you an intuition why in a second, by adjusting the pulses. And basically you can look up two papers there. One is PRL 118, 16401 from 2017. This is by Albert Rura. And also Christian, who actually initially developed the perturbative method, has also written a paper on this general mitigation schemes for how you can get rid of these initial condition dependent phases. And this is basically in PRA 103 0233 05, and this is from 2021. Okay, so the overall intuition in the compensation schemes, or in the simplest case, is basically the following: that when you have an interferometer, basically Z and T again, and you have pulses, 1, 2. What actually happens here is that you come in. Now I have to draw it right. So, and what happens is basically that in the second part, by actually the additional potential acting from the gravitational, from the gravity gradients, the interferometer trajectories don't cross at basically 0, t, and 2t, but they cross sometime later or sometime earlier due to the additional forces acting. And what you can do naively in the simple case here is you can actually adjust your pulse. So you basically take your last pulse and actually move it a bit to the side. And by that, you get a closed interferometer again. So this is the simplest case. You can also do more fancy stuff where you adjust the middle pulse and adjust also the K vectors to actually close the interferometer. But with these techniques, you can actually get rid of these dependencies again. However, you also, obviously, since you changed the geometry now, also have new phases in there. Okay, so I guess that's a good stopping point for today. Any questions?
About the gradients.
Yeah.
Put them like that, or are these the Christoffel symbols of weak field approximately?
Okay, so yes, the gravity gradients are actually the expansion, basically the Riemann tensor components, if you want. So Although the gravity gradients we're talking about here are basically the time-like part of that. So they are also basically, if you do the full expansion in GR, basically you get the time components, and then you also get the spatial components, which basically tell you how your local frame deviates from flat space. And these are also, well, act like these guys, but are not in here. So these guys we're talking about is just basically the time component of the Riemann tensor expansion, if you want. Yeah.
One nice question. Thinking that we are not considering any interaction between two wave packets in each path. If you would to take this into account, would you have to throw all of the form items to the middle or?
No. So I kind of tricked you a bit here, because you can go more general here. So what you would have to do if you have basically external potentials which are different on both paths, you basically just take the interaction picture we have taken with respect to the single external Hamiltonian and do an interaction picture with respect to the respective external Hamiltonian on the branch. So you could also basically by So what we have assumed here basically is that this guy here, right, H0 does not depend on the branch. So, but you can also actually make that guy branch dependent and can also make the perturbing forces branch dependent. And you can still do the calculation, it just gets more complicated, basically. So you can adapt this to the more general case where you really have path-dependent perturbations and even path-dependent zero-order Hamiltonians. That's why I initially said, so this is the case you can kind of solve analytically, but you could basically make this more general and then throw even numerics at the zeroth order thing to do the complicated stuff that might come up. Yeah. Okay. Good. Well, coffee break?
I have another question about
Yeah.
just like general interferometry.
I just have to stop the